Good evening. Okay. Good evening. Today we'll be looking at the third doubt class session for the course Interfacial Fluid Mechanics. Uh, Today, what I'll be doing is taking the solutions of week 1 and week 2 assignments. These are assignments from the previous years, and maybe some of the questions may overlap. But the idea is, if I give a solution for these questions, uh, you will be able to extend these questions to the current year, as more or less they are similar. So the agenda of today's class. Okay, so let's look at these questions. So I'll zoom in a bit. So week 3. Okay. So these are questions from last year. So the first question is, what are the units of surface tension? So this is a fairly simple question. Yet I'll discuss it briefly. So, so if I have a surface, make it blue. If I have a surface, then the surface tension tends to act only on the surface. And if we uh, look at the force at a cross section, if you look at the cross section, so we all know. So, so the force on this particular surface by the other surface to pull it in its own direction. Similarly, the force on this particular surface will be by the second surface, surface 1 and surface 2, by the surface 2 is to pull the surface 1 towards itself. So the surface tension acts only on the line. So we can write units surface tension are Newton per meter. That is force along a line. So this is a fairly simple question. So, so the answer will be A. Next, let me bring up question number two. So we have the question number two. So the question number says, consider a spherical drop of radius r of fluid A in fluid B. If gamma AB is the surface tension A and B, what is the expression of the capillary pressure jump across the surface? So we have a drop. We have a spherical drop. So we don't need the container. So drop of radius r. So the question says, what is delta P? So in the course, we have seen the Laplace pressure jump, which says that delta P is equals to gamma times R mean. So here it is given that gamma is gamma AB, and the R mean is supposed to be the mean radius, which is for a sphere just 1 by r by 1 by r, which is equals to 2 gamma AB by r. So 2 gamma AB by r. So that is C part. So the solution is C. So the answer is C. So let's look at the next question quickly. So let's look at the third question. The third question says, if there are five forces involved in a phenomena, how many unique non-dimensional numbers can be constructed? So let's look at this question. Let us assume for simplicity, let's work it out. Let us we have five forces. Let's say we have inertia force. It's much better. Then we have viscous forces. Then we have surface tension force. Surface tension force. And let's say we have gravity force. Hello. So we have inertia, viscous, surface tension, and gravity. So now there is no echo. Okay. Right. So there is no echo. Okay. And then we have the fifth force. Let's say it's electrostatic force. So now we know that to have non-dimensional numbers, let's say pi 1, it's simply we take two forces and then divide them, and that gives us a non-dimensional group. So let's say we have inertia and viscous, then we have pi 2 as inertia and surface tension, and then we have pi 3 as inertia and gravity, and then we have pi 4 as inertia by electrostatic. Once we have all of these, let's say we try to construct a fifth force, fifth non-dimensional group, and then we want it to be surface tension by viscous. So in order to get this, we simply can do pi 1 divided by pi 2, which is just inertia by inertia by viscous and inertia by surface tension, which gives us surface tension by viscous. So there we can see that if we have five forces involved, then trivially we will have only four non-dimensional groups that can be formed, and the rest of them can be just manipulated to get the others. So there are only four unique non-dimensional numbers for a set of five forces acting. So the answer is A. Let's go ahead and so the question says, what is the Weber number? The Weber number represents the ratio of which set of forces? So Weber number, So the Weber number is defined as inertia forces to surface tension forces. So these will appear generally in immiscible drops that are rising in a media. So when these drops rise up, we see these Weber numbers, and like a drop splashing on a solid plate where there is transfer of inertial force. So the potential energy essentially goes into the surface energy once it splashes. So these are areas where we see the Weber number come up. So that's the definition of Weber number. So the question says, let a scalar field f be defined as f of x comma y comma z, where x, y, z are the independent variables, and the expression goes as x square plus y square plus z square. Then the question asks, what is grad Laplacian of f? So the del square is called the Laplacian, and the question is asking us to solve del square f. Del square f. So we know that the Laplacian operator is del square del by del x square del by del y square plus del by del z square. So now we also know that f goes as x square plus y square plus z square. So trivially, del square f should be equal to 2 plus 2 plus 2, which is equals to 6. So the answer is 650 special. So the next question says, in continuum approximation, which of the below statement is true? So we'll go over the statements. The first statement says the interface needs to be treated as a region of finite thickness. The second option is the interface is treated as a mathematical surface with zero thickness. Curvature of the interface becomes negligible. Density does not vary in stress. So the last one is wrong. We have density variations when we are going from one fluid to the other, and curvature also in case of a drop or a surface with waves on it has a curvature. So the curvature is incorrect. So we have to decide between interface having finite thickness or considered as a mathematical surface with zero thickness. So the answer is that the interface is treated as a mathematical surface. The interface the interface is treated as a mathematical surface. So that's the next question. So the next question says, which of the below statements is true for a fluid-fluid interface for interface with surface tension? Pressure is always continuous across the interface. Pressure is always discontinuous across the interface. Pressure is discontinuous across the interface only if the interface has curvature. And pressure is continuous across the interface only if the interface has curvature. So you look at the Laplace equation again. So we know that del P is equals to gamma times gamma by R, R mean. So for the interface to have you said P outside. So for the interface to have a pressure jump, A, there should be surface tension and the surface needs to have a curvature. So the correct option is option C. Pressure is discontinuous across the interface only if the interface has curvature. So from the Laplace equation, we can say the pressure is discontinuous only if the interface has curvature. So we look at the next question. Next question. Yeah. So now we have the question, if tau is the stress tensor as defined below and n hat is the unit normal vector, then what is the expression for n hat dot tau dot n hat for the surface for the face A, B, C, D? So we're talking about this surface. So let's redraw the diagram. So we have A, B, C, D, and X. C. So this will be the n cap, n hat, and the n hat is just 100. So n hat vector is just 100, and then it's, so the question asks, find n hat dot tau dot n hat. So we'll write n equals to tau 11, tau 12, tau 13, tau 21, tau 20, tau 23, tau 31, tau 32, tau 33. So this will just be 100. We'll copy this. So by multiplying, first we'll get 100. then it will be. So the answer will be tau 1 1. Pretty straightforward. Now let's look at the next question. Ninth question. Question will be. So the question says, okay, we'll mark the answer first. So the answer is tau 1 1. Yeah. So the second question says, if the two-dimensional velocity field u given by 4x plus 3y I cap plus 2x plus lambda y j cap is solenoidal, what is the value of lambda? So given we have u, which is 4x plus 3y I cap plus 2x plus lambda y j hat. And then it is asked, um, lambda if u vector is solenoidal. So the condition that u vector is solenoidal simply states that del dot u will be 0. So replacing del by del x I cap plus del y j cap. So this is a 2D case, so we'll have only two components. Dot 4x plus 3y I hat plus 2x plus lambda y j hat. So the dot product gives 4 plus lambda, which is equals to 0. This implies lambda is equals to minus. So the correct option will be C. Let's look at the final question. So again, if tau is the stress tensor as defined below, n hat is the unit normal vector, and tau, t hat is the unit tangent vector for the face A, B, C, D. And the tangent vector t hat is parallel to the x-axis, then what is the expression for n hat dot tau dot t hat? So we have given n hat and t hat, and tau is given. We can copy our tau from here. this. And for the given surface, the normal is in this direction and the tangent is in the, therefore n hat is equals to 0, 1, 0, and t hat is again 1, 0, 0. So we have 0, 1, 0 multiplied by 1, 0. So if we multiply, we have tau 1, 1, tau 1, 2, tau 1, 3, which gives us tau 2, 1, tau 3, 9. So the answer is tau 2, 1. So the answer is tau 2, 1. So D part is all. So, so that brings us to the end of the first assignment. The assignment, although fairly simple, but we look at important aspects which are useful to the course. So I'll take a quick break and we'll resume by looking at assignment two. So mm, I'm feeling a little unwell, so I'll stop the class here. But if you have any doubts, please email me. Um, So I'll be stopping the class here today. There are no people here, but I'm feeling unwell. That's why I have to stop the class here. Sorry for that inconvenience.